Okay. Can you see my screen? Okay. So yeah, let's begin. Today's paper is developers' responsibility or database responsibility, rethinking concurrency control in databases. Now, what this paper actually does, it's more of a study of real concurrency bugs in the applications that rely on databases, right? So they look, I believe, at 46 different systems, identified 93 different bugs, and then they looked at what was the impact of the bug, what was the root cause of the bug, what was the mitigation, and then in the kind of later part of the paper, they discuss about how can we improve this whole situation with these bugs going forward. So let's first kind of focus on what are the concurrency bugs, at least especially in the scope of this paper, right? So they specifically talk about concurrency bugs in systems that rely on databases and the bugs that involve the database interactions, right? So in the context of this work, in the context of this paper, the concurrency bug is some kind of an issue that arises due to concurrent execution of two or more transactions. So yeah, it's a short paper, so I think I'll just dive straight into what they observe out of looking at these 93 bugs. At first they talk about the consequences of having the bugs. And the biggest category, the biggest consequence is data inconsistency, right? And within this data inconsistency, they identified a couple more causes that are very common. So miscounting and non-unique IDs. And this is actually non-unique ID is an actual example from the paper we discussed last week, right? So they had this as a bug, and the entire paper revolves around that bug. And well, out of 93 bugs that these people find, these authors found, 16 had this kind of problem. So yeah, last time I was saying, well, who makes those mistakes still? And apparently, quite a lot of people still, make those kind of issues. So they also have a big category of miscounting. And apparently, it leads to overselling for e-commerce platforms, right? So you may miscount the amount of inventory you have when you, subtract the inventory after each order, and you may go into negative, right? So you may sell more stuff than you actually had. They also talk about double spending. So they had examples where people were able to double spend promotion codes and things like that, and all because of the concurrency bugs. Yeah, a small, relatively small fraction of the issues actually resulted in unavailability of the system, right? So they, had 13 examples out of 93 that lead to crashes, freezes, or deadlocks, which I guess also caused the system to to freeze or whatnot. And 2 remaining issues right here. Yeah, the authors couldn't really figure out what was the consequence. So we know the issue, but we don't know what was the consequence. And moving on to the root causes. The biggest category in a root cause section of the paper, the biggest root cause, the most often root cause is read followed by relevant write. And again, that's the example that we had in the discussion last week, in the paper last week. Yeah, if you read something, do some kind of conditional on whatever you read, and then you update, let's say the same variable. Kind of as an aside here, the authors actually talk, about like how those things can happen. And apparently, that pattern where, just like in a paper that we saw last week, that pattern where like people use this like ad hoc transactions, right, where they don't put that same logic in one transaction, is quite common and often results in these kinds of mistakes. Another like decently big category for the root cause was inappropriate error handling. So that was a category that result in like maybe a crash and whatnot. So that's essentially not handling the exception and causing the failure, right? Causing the application to freeze or crash. And there were like a few other like smaller categories, like lock timeout, right? So waiting for things too much and then things timing out and just proceeding as the lock didn't exist. Unnecessary concurrent execution, interleaved consecutive updates, so kind of more intricate cases, and the other category, 22 cases in 22 bugs that the authors couldn't really identify a root cause because like there was not enough information in the reports and whatnot. And on the fixes side, I think the most common fix that the authors talked about was using select for update, which essentially logs the rows returned by the select until the entire transaction that the select is part of, that query is part of, has been committed. So that's essentially adding locks, but this locking exists at the database level. And the second most common fix is additional locking, but those are the locks that may exist at the application side. So yeah, like these two first fixes, they are really about locking the data and just managing that concurrency that way. Uniqueness constraints, that was another kind of important category of fixes, right? So if you expect a column in a database to be unique, add that uniqueness constraint, right? Which again surprises me why it wasn't really the case in those 8 situations in the first place. Additional versioning, that one I found quite interesting because apparently here the applications and systems implement the versioning or implement some kind of concurrency control on top of a database, right? So they implement the versioning at the application level. Stronger isolation was only 7 cases, right? So yeah, the thing that I forgot to mention is like a lot of those bugs, they happen because the real systems don't run at the strong isolation levels. And in fact, a lot of them run at like read committed and whatnot. So you would think that trying for like stronger isolation may fix a lot of them, but that was the solution only in 7 cases. And I think it should be quite obvious why, right? People don't want to pay the price of like the performance and whatnot. Serial execution. So there were a few bugs that they found where transactions were expected to like execute serially at the application level. So like you finish one and then another, but instead they were not, right? So they used some kind of ordering procedure to like order those transactions, which again, interestingly enough for me, involved like using external serializer, like having a queuing system that that was used to order those transactions. Additional, if checks, weaker isolation. That was also interesting, and I think that was the solution in some of the bugs that caused like some of the timeouts and stuff. So performance issues, the weaker isolation may have helped there. Another good category is do nothing. So kind of catch an error, catch an exception or whatnot, and just pretend it never happened. And one use case that they found was fixing the data inconsistency by business procedures, right? So if you screwed up something, just change your business procedure so you don't screw up next time. And the other was like 20 other bugs that don't really fit in any of these categories. Okay, so that's kind of the bulk of the paper. They in the paper they tried to.
Alexei, what was that weaker isolation fix mean? I mean, both stronger isolation and weaker isolation is a fix. Can you tell about the weaker isolation? Did I miss it?
Yeah. No, stronger isolation, right? So that's one fix. Weaker isolation. Yeah. So sometimes they have those issues like lock timeout, right? So and that is because they run at this stronger isolation, let's say serializable and whatnot, and they just like the performance is bad, right? So because of the concurrency, things start to like lock out for too much, right? So to fix the performance issues, you really degrade your isolation level.
I see. So this is less of a correctness issues, but more of things getting blocked. So they realize actually we could have chosen a weaker isolation or break a transaction and stuff like that. Okay, got it.
Yeah. So the paper kind of at the beginning they posed this like 3 questions. Do weakly isolated or ad hoc transactions actually cause anomalies in real-world applications? The quick answer is yes, right? So the long answer you can read in a paper, but I think it still boils down to pretty much just yes. So I'm like really surprised about this ad hoc transaction part, right? So that's when the applications like they don't use they implement their like transactional logic as multiple transactions and try to manage how those transactions execute themselves, right? Again, that's the example from the paper last time. So yeah, they found that they cause problems. Surprise. How much effort does it require to handle anomalies in real-world application? Quick answer is a lot. I think their longer answer is kind of broken down into different stages, like where do you spend time? So finding the issue is time consuming, but they also say like the most time consuming part is actually implementing the fix, because most of the like from the reports that they observed, like most of the initial fixes are not correct and can actually cause even more problems. So the entire process of actually finding the fix for a lot of these bugs is the most time consuming part, right? So the third question is why not use serializable or like use more locks and whatnot. And the quick answer is it takes time, right? It hurts you long locking. So what can we do? Quite frankly, I'm not sure like I fully understand the logic behind that section in the paper, right? So the short term is use snapshot isolation, because that will fix a lot of the issues that they observed, right? So the paper goes into more details why, and use unique constraints, which again seems like a no-brainer to me. So that's something for the short term. Now the longer term, the authors spend a lot of time thinking about automatic analysis of like code analysis and whatnot, and trying to figure out the concurrency through this analysis and optimize for maybe transactions that can run concurrently, transactions that need isolations, transactions that don't need isolation, transactions that need to be serialized, which, a whole like other, issue here. And they say that, hey, maybe that's the future. So yeah, this is about as much as kind of I want to go into that. Yeah.